So this is about our Practically app. Okay, Practically is the only hands-on learning app for 6th to 12th grade where you can learn maths, science concepts visually and with the 3D model. Okay, for that you have to download our app from the Play Store. This is the interface on your screen right now. Let's begin. Let's start with the covalent bond. See, covalent bond is the most important bond in the chemistry. No bond is more important than the covalent bond, because most of the compounds contain covalent bond only. Okay, covalent bond containing compounds are very huge in number. Okay, let's start with it. So the very first concept, the very first theory of covalent bond is a wave mechanical concept. In wave mechanical concept, what we have is that one orbital can accommodate at the most 2 electrons with the opposite spins. That means the one single orbital cannot accommodate 2 electrons with the same spin. For example, suppose if you have just a minute, there is some problem with this. Wait just a minute. Okay, so what I was saying, one orbital can accommodate at the most 2 electrons with opposite spin. That means if you have orbital like this, the 2 electron cannot exist like this, or they also cannot exist like this. This is the wrong way. They will only exist as like this. This electron spin up, spin electron spin down. That is the orbital. That's how it is. So one orbital can accommodate at the most 2 electrons with the opposite spins. Half-filled orbital. Half-filled orbital or unpaired electron. Orbital accepts 1 electron from another atom to complete its orbital. For example, if you have hydrogen, single electron, so another hydrogen can accommodate this with having opposite spin like this to form a H2 molecule. So in the case of hydrogen, you complete the duplet. Okay, so that's how it is to it completes orbital. Okay, for the other atoms we will see as we'll move forward. Okay, so third, the tendency to complete orbital or to pair the electron is a condition of a covalent bond. Covalent bonds most important condition is what? Is to complete orbital or to pair the electron. So orbital should get complete or electron gets paired. That's the only condition of a covalent bond. Completion of octet, as we had seen in the last lecture, if you remember, we had seen the octet rule there. Okay, so completion of octet is not the essential condition. Remember this. It is not essential condition of a covalent bond. That is the main summarized point here. Okay, octet can be completed, octet can be expanded, octet can be contracted also. That is not the thing. The orbital and electrons should get paired. That's the condition. So let's move ahead. Theories of covalent bond continuing, wave mechanical concept. So that is what with the hydrogen and the other atom. What about the other atom which shows variable valencies? Variable valencies are shown by those elements which have empty orbitals, in the outermost shell. So to show variable valency, you need to have empty orbital. For example, let's take the example of phosphorus. Atomic number 15. Okay, if you write its electronic configuration, it would be like neon 3s2, 3p3 and 3d0. So 3d0 because there are no electrons in d orbital. Okay, for the s orbital you got 2 electrons here. For the p orbital you got another 3 electrons here, and your d orbital is empty. So see, every element always shows those many number of valencies, the number of unpaired electrons. You can clearly see here the unpaired electrons. Unpaired electrons are how much? This is the unpaired electron. There are 3 unpaired electrons. So phosphorus valency is 3. It is always 3. Okay. But phosphorus also shows valency of 5. It also shows valency of 5. How does it show valency of 5? By promoting this electron into this d orbital. Okay, so if the empty orbital is there, then only you have a variable valency. Okay, we will see that ahead. Next, the lone pair electrons. The lone pair electron gets excited in the subshell. In the subshell of same shell. Lone pair electron gets excited in the subshell of same shell to form a maximum number of unpaired electrons, so that it could show maximum covalency. In other words, maximum covalency will be shown only in a excited state. For example, let's take this carbon. Atomic number of carbon is 6. So its electronic configuration is 1s2, 2s2, 2p2. Okay. This 1s2 never takes part in the bonding. Okay. For 2s electron, you have like this and 2p2. So you have 2 electrons here, and we know, so your carbon is having 2 unpaired electron here, right? You can see that here. But we knew that carbon's valency is never 2. It is always 4. So how 4? So this lone pair gets promoted to the subshell of same shell. Which is same shell? Second shell. And it goes from S to P. S and P are what? S and P are subshells. So that is what the point is. The lone pair of electron gets excited in the subshell of same shell to form maximum number of unpaired electrons. That is how covalency is shown in the excited state. Okay, the energy required for this excitation of electron is called as promotion energy. Why I'm saying promotion energy? Because your 2s is slightly below 2p. It is slightly below 2p. Okay, so electron requires energy to go from S to P. Okay, that is why it is called as promotion energy. And what is promotion rule? Promotion rule is excitation of electron in the same orbit. What is meant by same orbit? That means electron always get promoted. It goes from S to P. Okay, but this 2 number will never change. That means electron will never go from 2s to 3s. Electron never goes from 2s to 3s. No. Or it also cannot go from 2s to 3p. This number should be same. The second number, which is called as principal quantum number, it should always be same. Orbital can change. S, it can go from S to P, it can go from S to D. That can be changed. Okay, but the second number cannot be changed. That is the rule. Okay, chalo. Let's move ahead. Everyone clear with this? Does anyone have doubt here? Hi, Manoj Kumar, no doubt. Okay, very good. If you understood it, very good. Chalo, let's move ahead. So I was saying, look, if you write the electronic configuration of phosphorus, its atomic number is how much? Its atomic number is 15. So if you write its electronic configuration otherwise, it would be 1s2, 2s2, 2p6, 3s2, 3p3. This 1s2, 2s2, 2p6, these all are equal to neon. That is 10 electron. And that neon act as a inert shell kind of. So it will not involve in the bonding. The bonding will be only involved with the outer shell, which is also called as a valence, also called as valence shell. 3s, 3p3 and 3d0. 3s2, 3p3, 3d0. Okay, so you can write this like this: 2 electrons, okay, and 3p, you have 3 electrons. So these 3 electrons now combine with the chlorine's electron. Okay, it can combine with the chlorine's electron like this: chlorine, chlorine, chlorine. They will be paired up here, and that's how you can form PCl3. Because there were 3 unpaired electron only, so that's why 3 chlorine could bond there. That's why phosphorus covalency is 3 in ground state. In ground state, it always shows valency 3. But now, what happens in excited state? In excited state, these electrons, the electrons that you are seeing here, gets promoted to empty d orbital. Look here. This electron, you have an empty d orbital here. It is like this. You have a 3d that is always empty. Okay, so if you do not give any energy, it will stay as it is. But in excited state, what happened? This electron pair gets promoted to where? Empty d orbital. So here you got single electron now with the s. 3 electrons of p were already there. Now you have 1 electron in 3d. So now you got 5 unpaired electrons. So now in the excited state, your phosphorus can show valency 5, because how? You got 5 unpaired electron now, right? So 5 chlorine would come here like this. So that's how PCl5, you can see it is showing valency 5. Okay, everyone clear with this? Okay, so we can move ahead now. See, let's look at the sulfur. Now, sulfur's atomic number is how much? Atomic number of sulfur is 16. So how would be its electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p4. Again, this 1s2, 2s2, 2p6, it is equal to 10 electrons, which is equal to your neon. So that is going to be inert core. Okay, this is your valence shell. So here will be bonding happen. So you have 2 electrons in 3s. You got 4 electrons in p. So you have 3s2, 3p4. Okay. Now you can see you got only 2 unpaired electrons here. Look, this is first, this is second. Now your sulfur is in ground state. It is not excited, it is in ground state. In ground state, your sulfur has only 2 unpaired electrons, right? So here your sulfur can only show valency 2. So that's how 2 fluorine can come here with their unpaired electron, and it can show valency 2. Okay, clear? Let's move ahead. Now suppose the sulfur gets excited to its first excited state. Now what happens in first excited state? In first excited state, if you come from the outside, this is outside. Let me tell you, this is your outside. Okay, from here you're going inwards. So as outside, you cannot touch the s electron directly. Your p electron, because if you go from outside, which orbital comes first? The p orbital comes first, right? P orbital comes first. So therefore, this in second excited state, this pair gets promoted to your empty d orbital. So what happens now? Look here. I'm just telling the process there, but I'm doing it here. 1, 2, 3. Now you got 4 unpaired electron. So now you have 4 unpaired electron in the very first excited state. Okay. Now, since your sulfur in your first excited state has 4 unpaired electron, now it can show valency 4, right? So now your fluorine can come here with their unpaired electron to form a bond. So that's how your fluorine can show valency, covalency 4 in the first excited state. Okay, clear everyone? Yeah, Sajid, we will see the hybridization later on. Okay, this theory is not of hybridization theory as such. Okay, so let's move ahead. Any doubt here? Okay, no. Let's move ahead then. See, this is the second excited state. Now, what happens in second excited state? In second excited state, your P is left with the no unpaired electron now. Sorry, no paired electron, right? So now your 3s electron will get promoted. And after promoting, now you have 6 unpaired electrons. Now you have 6 unpaired electrons in the second excited state. Now your sulfur can show valency 6 by combining with 6 fluorine atoms. Now the fluorine atom will come here. They'll form a covalent bond like this. Okay, that's how you form SF6. Here your covalency is how much? It's a 6. So what are the variable valencies of sulfur? Variable valencies of sulfur are 2, 4 and 6. So you will always find sulfur forming 2, 4, 6 bonds only. It cannot go beyond 6. Okay, its valencies are even. Its valencies are even. That's how sulfur shows the valency 6. Okay, clear everyone? Shall we move ahead? Okay, sure, very good. So now next is our iodine. What is the atomic number of iodine? Atomic number of iodine is 17. So its electronic configuration again comes like 1s2, 2s2, 2p6, 3s2, 3p5, 3d0. So that's how you have 10 electrons here. That is equal to neon. Okay, and this is your valence shell. So we are not talking about inert core again. Okay, 2 electrons in 3s, 5 electrons in your p. So look, in the ground state, how many unpaired electrons are there? You can see only one unpaired electron there, right? So in the ground state, covalency of your iodine, is 1, right? Iodine can form only one bond. For example, it can combine with fluorine like this to form CLF, sorry, not CLF, IF. It can combine with the fluorine also to give you ICL, or it can combine with the hydrogen to give you HI. That's how your iodine can show valency 1. Okay. Now you tell me, sorry. Sorry, valence. Oh, atomic number of iodine is not 17. Sorry, everyone. It's a 53. It's a 53. But I was talking about this core. This core is 5s2 and 5p5. It is 5s2 and 5p5. After that, you have 5d0. Okay. So I was actually talking about the chlorine there, but anyways, so this is 5s, 5p, and 5d. Okay. Now, iodine and chlorine and fluorine, all of them have similar electronic configuration. I'm saying similar, not same. Okay. It is a different electronic configuration, obviously, but only this number is different, which is your 5. In bromine, it's 4. If you have taken bromine, it would have been 4s2, 4p5. For the chlorine, it's 3s2, 3p5. For fluorine, is 2s2, 2p5. Okay. Okay. Sure. Now, so you can see your iodine is having one unpaired electron only. Okay. So it can show valence covalency 1. Now, suppose if I promote this electron, can you tell me what can be the covalencies of your iodine? What can be your variable valencies? Yes, Sajid, you are right. It's 1. But apart from one, what can be variable valencies of iodine? 5s2, 5p5. Okay, and you have a D here. D is empty. Okay, so yes, Sajid, you are right. So we can promote this electron, right? As I told you, the p electrons, p orbitals electrons get promoted first. So you can promote this electron here, and now you have how many unpaired electrons? Now you have 3 unpaired electron. Now you have how many? 3. 1, 2, 3. So iodine can show covalency 1, then 3. After that, this pair will be promoted, and then you will have 5 unpaired electron. That is in the second excited state. Okay, and then there comes the third excited state where this pair will also get promoted to here, and then you will have covalency 7. So variable valencies of iodine are how many? It's 1, 3, 5, 7. Okay, so what did you observe? The variable valencies between sulfur and iodine. Chlorine also shows in a similar way. Okay, instead of iodine, you can also take the chlorine there, no problem with it. So the variable valencies of halogen are odd in number. For the sulfur, it was even number. For the halogen, it's a odd number. Okay, so that's the main difference I was pointing out to you. Okay, so let's move ahead. Now there comes the valence bond theory, the most important theory, that is your valence bond theory. Okay, this is the most celebrated and most important theory of all. Okay, so there are valence bond theory has been divided into two ways. One is your overlapping theory. Okay, another is our hybridization theory. Hybridization theory we will see shortly, obviously, but let's see first overlapping theory. What is overlapping theory? It was presented by Hitler and London. Not the Hitler you are thinking, okay? It is not a German Hitler. It was presented by Hitler and London to explain how a covalent bond is formed. Okay? The main points of theory are, see, to form a covalent bond, overlapping occurs. So here, overlapping occurs between half-filled valence shell orbitals of two atoms. So overlapping is very important here. Okay. How is the overlapping? That's how the overlapping is. This is how. This is the one orbital. This is another orbital, and they overlap like this, like this. So that is called as overlapping. So to form a covalent bond, overlapping is must between the orbitals. Okay. Second, a resulting bond acquires a pair of electrons with opposite spins to get stability. We have talked about this earlier also, that resulting bond always acquires a pair of electrons with opposite spins. Okay, that's the point we had already covered. Let's move ahead. The orbitals come closer to each other from a direction in which there is a maximum overlap. Okay, orbital always come from that direction where the overlapping is maximum. For example, let's take example of this orbital. See, you have an orbital like this. Okay, and you got another orbital. So these two orbital will never come in the following way. The way I have shown it to you, that this and this, no, this will never happen. They will always come like this. This are one orbital plus you got another orbital. So both of them comes together and you get the orbital like this. See, that's how they comes. They'll always come either in this way or they will come like this and they will give you this. What do we call this and what is this? That we will say later on. Okay, but for the time being, orbital come closer to each other from the direction in which there is a maximum overlapping. So that's the way. This is not the way. They will never come in this way. Okay, clear? Understood? Okay. If you have any doubt, you can ask me. Okay, chalo, let's move ahead then. Chalo. So overlapping theory continues. As I was saying, orbital comes from that direction where overlapping is maximum. Secondly, since it comes in that way, covalent bond always has a directional character. Covalent bond has a directional character. Your ionic bond will never have a directional character. Why? Because in ionic bond, what happens? And that this is Na plus, Cl minus. See, this charge is spreaded over the entire NaCl. So you can't give a direction to it. But covalent bond has a direction, as we had seen with the overlap. Okay. Next point. Extent of overlapping is directly proportional to the strength of chemical bond. That means more the overlapping, more is the strength of a chemical bond. For example, if you have overlapping like this, so this overlapping would be stronger. This overlapping would be stronger than this overlap. This is our axial overlapping. This is axial overlap. Okay, this is sideways. This is sideways or lateral overlap. This is sideways or lateral overlap. So this is weak overlap and this is strong overlap. So strong overlap will give you strong bond. Strong overlap, strong bond. Weak overlap, weak bond. Okay, so the extent of overlapping is directly proportional to the strength of a chemical bond. Okay, extent of overlapping depends on two factors. So let's talk about that. Your extent of overlapping depends on two factors. What are two factors? First is nature of orbital. So there are four types of orbital, as you know: S, P, D, and F. Okay. Out of these four, your P, D, and F, these are directional orbitals. These are directional orbital. So the directional orbital always shows more overlapping. And the only orbital that is your s orbital is what? It's non-directional. So since it's a non-directional, it would show less overlapping. Okay, remember that always. So the orbital which has the directional character shows more overlapping. The orbital which is non-directional shows less overlapping. So between your S, P, D and F, S shows the less overlapping, P, D, F shows the more overlapping. Okay, that is what the nature of orbital. That is the first factor. Okay, second factor is what? Is the nature of overlapping. How is your overlapping happening? Okay, you can see here this first one I told you, coaxial overlapping. What is coaxial overlapping? This is your coaxial overlapping. I shown here. See, this is coaxial overlapping. So coaxial overlapping, in the coaxial overlapping, extent of overlapping would be more and hence the bond would be more strong. With the collateral overlapping, what is collateral? This is the collateral. This is our collateral overlapping. I wrote here now lateral, that is collateral. So in collateral overlapping is less. Why? Because the contact is not that stronger as much as it is in a coaxial overlapping. Okay? So for the coaxial overlapping, extent of overlapping is more, hence the bond is stronger. For the collateral overlapping, extent of overlapping is less, hence the bond is weak. Okay? So let's take the order of strength of coaxial overlapping. See, if you have PP, PP is highest, SP. What is the meaning of this? So as I told you, see, in the given combination, both P and P are there. That means both are directional. If the both are directional, the strength of overlapping would be more. That's why in PP, the PP overlapping is the strongest. Between S and P, only P is directional. S is non-directional. So overlapping is weaker than what it was in PP. As far as SS is concerned, for SS, both are non-directional. That is why the order of strain for coaxial overlapping is highest in PP, second number in SP and third number in SS. Okay, clear to you now? PY Natikar. Who told you beta this is grade 3? This is not grade 3. This is grade 11 and 12th. Okay? Is this clear to you all now? Shall I move ahead? Okay, Sajid, chalo, very good. Let's move ahead. See, as I was telling you, overlapping theory. See, so this is the complete coaxial. Okay, you can see this is complete coaxial overlap. You can say this is also coaxial, but you can see the extent of overlapping here. It looks quite strong here than here. Here it is more strong than this. Okay, and lastly this. Here it appears to be stronger. Okay, but both are non-directional. Both are non-directional, which makes overlapping weak. Here this is directional. This is non-directional. That is why the overlapping is slightly weaker than the PP overlap. That's why you have a strongest overlap here, then here, and then lastly this. That's how the order goes. Okay. And the next point, as the value of N increases, the bond strength decreases. Mind this point as the value of N increases, the bond strength decreases. Look here, I'm showing you here 1s, 2p, 2s, 2p, 3s, 3p. So what happens as the number increases, the density with which electrons are packed decreases. As the density with which electrons are packed decreases, obviously it will weaken the bond. Okay, so as the number n increases, the bond strength decreases. The second reason for that is the distance. For example, look here, hydrogen, fluorine, this is the bond distance. Okay, now this is not exact bond distance, I'm just showing you for example. If you take hydrogen, fluorine, it would like look like this. If you take hydrogen, bromine, it would look like this. If you take hydrogen, iodine, it would look like this. Now hydrogen is constant everywhere. Okay, for hydrogen you have taken what orbital? 1s, 1s, 1s. For fluorine it's what? 1s2, 2s2, 2p5. It's 2p, is 3p, is 4p here, and lastly it's 5p here. So this n is increasing, right? This n is 2 in fluorine, 3 in chlorine, 4 in bromine, and 5 in iodine. So as this n increases, you can see the bond length is also increasing. So as the bond length is increasing, obviously the force of attraction between your hydrogen and this, here it's iodine, here it's bromine, here chlorine, and here fluorine. So this force of attraction also decreases because distance is more, no? So as that force of attraction decreases, it makes the bond further weaker, and that is why as the value of n increases, the bond strength decreases. Remember this point. Okay, next, if the n is same, n means what? This is your n, second, यहाँ पे second, everywhere n is same. If the n is same, then you need to look at the orbital. And as I told you earlier, if the orbital is directional, obviously strength will be more. Here both are 2p, I mean both are 2 2, but here the orbital is p. Both are directional, right? Both of them are directional. Here only p is directional, s is not directional. Here both are non-directional. That is why if the n is same, you need to go for the orbital. Okay, clear everyone? Understood everyone this point? Okay, so let's move ahead then. So overlapping theory, we are continuing with it. The electron which is already paired, in valence shell can enter into bond formation if they can be unpaired. Electron which is already paired in valence shell can enter into bond formation if they can be unpaired first and shifted to vacant orbital of slightly higher energy of the same energy shell. We had seen that here. See, this electron is paired in sulfur, in S, okay, and it is belonging to the same shell, third. So this can be unpaired and can be promoted to the next higher energy level because 3D is upper, 3D, then 3p, and then 3s. Okay, so basically you are promoting electron from here to here. Okay, 3D, 3p, 3s, like that. So that is what that point was saying, that electron which is already paired in valence shell can enter into bond formation only if they can be unpaired first and shifted to vacant orbital of slightly higher energy of the same energy shell. Okay, now this point can explain the trivalency of boron. How? Look at this. The atomic number of boron is 5. So its electronic configuration is 1s2, 2s2, 2p1. So you got 2 electrons in S, 1 electron in P. Okay. Now we knew that valency of boron is how much? It's 3. But you can see here, you got only one unpaired electron, right? So you got only one unpaired electron. That means valency of boron should have been 1. But we knew it is not 1, it's 3. So what happens? Again, this electron pair gets promoted here. And now you have what? Now you have 3 unpaired electrons. And that's how your valency of boron now becomes 3. So this point can explain the trivalency of boron, tetravalency of carbon, which is 4, and pentavalency of phosphorus, and also hexavalency of sulfur and heptavalency of iodine. We had seen that earlier, right? Okay, sure. So there are 3 types of bond on account of overlapping. Okay, how does overlapping happens? How does overlapping happens? Based on that, there are 3 types of bond. One is sigma, another is pi, another is delta. You can also write it like this: sigma bond, okay, ऐसे झुका हुआ 6. Then you got the pi bond, sigma, pi bond, and lastly you got the delta bond. So that's how you have 3 types of bond: sigma, pi, and delta. Okay, let's see them one by one. First, sigma bond. So how does sigma bond forms? See, when orbitals overlap along their internuclear axis, whenever orbital overlaps along their internuclear axis, sigma bond is formed. Internuclear axis means what? See, if you have a s orbital, you can see here, this is s orbital, half electron. This is the example of hydrogen, hydrogen, hydrogen. Okay, and this is what? 1s, right? 1s, 1s. So you got this electron, both of them both of them gets paired here. You got the hydrogen molecule. SS overlapping. That's how you form a sigma bond. But sigma bond not necessarily formed only by SS. It can also formed by SP. How? This is one electron, and then you have another electron in the p orbital. This is your nucleus in the center, and this is your what? This is your internuclear axis. This is your internuclear axis. So electron is downward, and now both of them overlap like this. So that's how you get the SP overlap. Okay. Lastly is PP overlap. Now PP overlap, as I told you, the only axial overlap of P and P. Okay. This is your P. One electron here. Another electron here. Both of them overlaps like this. And that's how you get the PP overlap. So this is internuclear axis. Okay, this is axial overlap. Sideways or lateral overlap, that we will see later on. Okay. Apart from that, you also have a sp3s. sp3s means CH4. In CH4 you have sp3s overlap. sp2s. In ethylene, CH2, the carbon hydrogen overlap here is sp2s. Then sp3, the CH3. Here the carbon overlap is sp3, sp2, CH3, CH double bond CH2. Here this carbon is sp3, this carbon is sp2. So this overlap is sp3, sp2. Okay, so all of this, and sp also. sp means what? sp overlap. sp overlap, yes. Show you this. See, triple bond. Here, this happens in alkyne. So between this carbon and this carbon, this overlap is what? This is our sp overlap. So double bond is sp2 with the between the carbon, and between carbon and hydrogen it's sp2s. We will see that later on. Okay. Right now I'm only telling you how many types of sigma bond are there. Okay. Clear everyone here? Okay. Chalo, if everyone is clear, let's move ahead now. So, overlapping theory. How sigma bond is formed? As I told you earlier, this is how your coaxial overlapping happens between the internuclear axis. This axis is what? This is your internuclear axis. So if the overlapping happens along with this, it is called as pp coaxial overlapping. That's how your sigma bond actually gets formed. Okay. Then you have when two p orbitals overlap laterally, when two p orbital overlaps laterally or sideways, the pi bond is formed. So this is how they overlap sideways. I have shown it to you earlier also, right? So this is how you form a pi bond. That is your pi bond. And this overlap is what? This is our lateral or sidewise overlap. And this always gives you pi bond. And you can see here the extent of overlapping. The extent of overlapping here is less, but here it's a more, and that is why the sigma bond is always stronger than a pi bond. Sigma bond is always stronger than a pi bond. The strength of this bond is always higher. Okay, clear everyone? I'll give you some time for a doubt if you have any. Yeah. Yes. Yes, Sajid. PP, PS, and SS all are sigma. PP can give you sigma also and pi also. PS will always give you sigma and SS will also always give you sigma. Okay. Shall we move ahead? If you have any doubt, you can ask me. No? Okay. Chalo. So the last bond that we have is delta bond. How do we form a delta bond? See, it's a special type of bond, okay, where the lateral overlapping happens between the four lobes of d orbital. When the lobes of d orbital overlap laterally with another similar d orbital, you produce or you get a delta bond. That's how you get the delta bond. So how the dx square dash y square orbitals are? You can see here the dx square dash y square. See, they look like this. This is your x and this is your y. Okay, electron density is like this. Then you have another dx square dash y square. So their orbital, this overlap from that side. I cannot show you here, but you can see it here. You can see it here clearly. So if you take the opposite side of this and opposite side of this, they will overlap from that side. That's how they overlap laterally. This is the rare case. Okay. This is the rare case. It does not happen always. Okay. So clear with you where does the delta bond forms? Okay. Okay. Chalo, let's move ahead then. Next is hybridization theory. So there are two theories of VBT. First one was overlapping theory. Second is our hybridization theory. Okay. The hybridization theory, it was introduced by Pauling and Slater. Okay, Linus Pauling. His name was Linus Pauling, and he also had won a Nobel for this. He also had won a Nobel for this. Okay. Now, to explain this, you need to know I mean, this theory was actually introduced to explain the equivalent nature of covalent bonds in a molecule. Okay, because every bond that you have in a covalent bond is equal. You will never see that some bonds are weak, some bonds are short. I mean, in some cases it does happen, okay, but in maximum cases all the bonds are equally strong. Okay, so let's take example of why hybridization was needed. Let me take you the example. Let's take the example of carbon, for example. Okay, carbon's atomic number is 6. Everyone is known with it, right? You have 1s2, 2s2, 2p. So in the ground state we had 2 electrons here. Okay, so what happens in excited state? This electron gets promoted here. We knew that already. So you have 1 electron here and 3 electron here. 1, 2. So now you got 4 unpaired electron. Now you got 4 unpaired electron. Now you can clearly see here 1 electron is belonging to S and other 3 are belonging to 2p. So if the hydrogen comes now, how would it look like? See, this is your carbon. Okay, and another is this. So this 3 bonds, hydrogen, 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 and the 4th bond would be this one. So that means this bond should have been shorter. This bond should have been shorter and this bond should have been longer. In that case, what would happen? These 3 bonds would have been weaker and this bond would have been strong. But that is not the case. In reality, that is not the case. All the 4 bonds are equally strong. This is not the structure actually. This is wrong. This is also wrong. In reality, it is like this. Carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, and carbon, hydrogen. All the 4 bonds are equally strength. They are equally long. So how to explain that? How to explain that? Not only there. Look here. The example is given to you. Beryllium. Atomic number of beryllium is how much? It's a lithium will have, it's a 4, right? So electronic configuration is 1s2, 2s2, 2p0. Okay, again in the ground state you are having 2 electron here and you do not have any electron in p. That is your ground state. In excited state, electron gets promoted from here to here. It is like this. Now you are having 1 electron in S, 1 electron in P. Okay. Now if the chlorine comes, for the chlorine it's a p orbital only, right? But for the beryllium, one is S, another is P. So that's why you can see here one is P for chlorine, S for beryllium. P for beryllium, P for chlorine. So the bond would have been like this, PP, PL. You can clearly see here, this bond is shorter. Look at this. This bond is shorter than this bond. Okay, so it would have been like that. But in reality, it is not like. In reality, beryllium and chlorine bonds are equal long. They are like this. So both the B and Cl bonds should have different parameter. The PP bond should have been more stronger than SP bond. Okay. So, but in reality, in practically, bond strength and distance of both the B and Cl bonds are exactly same. It is exactly same. Same is the case with the four bonds of carbon and hydrogen. So how to account it? Okay, how to account it, how to explain it? And that is why the hybridization theory came into existence. What does this theory tells you is that this S and this P, they combines together. This S and P combines together to give you new set of orbitals, which are called as hybrid orbitals, which are equivalent in size, shape, energy, only they are different in direction, which is obvious. Okay, as a human, we also have both the hands exactly similar, but direction is different. No, we cannot have both the hands on one side. The same thing happens here. S and P orbital, they combine, they mixes together, they mixes and they gets recasted into new set of orbitals, which are called as hybrid orbitals. Those hybrid orbitals are same in size, shape, energy, only they have different orientation in a space. Okay, so let's see how does it goes. Okay, so what is the definition of hybridization theory? See, it is a mixing. It's a mixing of different shapes and approximate equal energy atomic orbitals. Approximate equal energy atomic orbitals. Why I'm saying approximate? Because look here, between 2s and 2p, we know that 2p is slightly upper in energy than 2s. 2p is slightly higher in energy than 2s. So that is why I'm saying mixing of different shapes and approximate equal energy atomic orbital, and the redistribution of energy to form a new orbitals of same shape, same energy. And these new orbitals are called as hybrid orbitals. And the phenomenon is called as hybridization. That's how the hybridization theory came into existence. Okay, so as far as beryllium is concerned, let's see how things happens in beryllium. The atomic number of beryllium is 4, as we had discussed earlier. So let's not talk about 1s2. Let's see only 2s2, 2p0. That's in ground state. Right? It would look like this. In excited state, electron gets promoted from here to your p. Now you have electrons in s as well as p. Now this gets mixed. Now this gets mixed together to produce new set of hybrid orbital called as sp orbital. Now always remember, the number of atomic orbital combines are equal to number of hybrid orbital produced. So since we have combined two orbitals, one s and one p, you will get two hybrid orbitals called as sp. So that means your beryllium will produce two orbital. This is also sp. This is also sp. You have one electron here. You have one electron here. Now chlorine will come. Now chlorine will come and overlap with this like this. Chlorine. That's how you form sp and p. Chlorine is p, no? spp, spp, and both these bonds are equal. That's how the hybridization has explained why the bonds are equal in strength. Okay, clear how hybridization theory works? Okay, let's move ahead with this now. See, what are the characteristics of hybridization? Hybridization is the mixing of orbitals. Mind this point. It's a mixing of orbitals, not the electrons. It is a mixing of orbitals, not the electrons. Your electrons are not getting mixed here. Orbitals are getting mixed. Okay, and therefore, in hybridization, full filled, half filled, and empty orbitals may take part. Okay, here orbitals are getting mixed, not the electrons. So therefore, any orbital can be mixed. Orbital may be full filled, half filled, empty orbital. Because in the earlier theory, what did we see is that orbital can only be combined if it has a unpaired electron. Remember, orbital can be combined with another orbital only if it had a unpaired electron. If it has a paired electron, it cannot be involved in a bonding. Okay? But hybridization says all the orbitals, may be it a full filled, be it half filled, be it empty, it can mix. Okay. Next, number of hybrid orbitals formed is always be equivalent to number of atomic orbitals which have taken part in the process of hybridization. Number of hybrid orbitals formed will always be equal to number of atomic orbitals which are mixed together. This is the one point I told you earlier also. Next, each hybrid orbital having two lobes. One is larger, other is smaller. We will see that shortly, how one is larger, another is smaller. The bond will be formed from a larger lobe. That means we just now saw the beryllium, it produces the sp orbital, right? So it gives you this one larger, okay, and another one is a shorter, smaller orbital like this. Larger, smaller. So this large will be combining only, not the shorter. Okay, I'll tell you that as we move ahead. Okay, I'll tell you that. Let's see some of the facets of hybridization theory. See the number of hybrid orbitals on central atom of molecule or ion. The number of hybrid orbitals on central atom of molecule or ion is equal to number of sigma bonds plus lone pair of electron. Number of hybrid orbitals on central atom of molecule or ion is equal to number of sigma bonds plus lone pair of electron. For example, look at this NH3. Now in NH3 you have one lone pair, okay, and 3 sigma bond. This 1 sigma, 1 sigma, 1 sigma. So 1, 2, 3 plus this 1. How much is the number? Number 4. And 4 number corresponds to sp3. If the number comes 3, is sp2. If the number comes 2, is sp. A number will never come 1. Okay. So for 2, because there are two orbitals here, that's why number 2 sp. There are 3 orbitals here, that's why sp. 4 orbitals, sp2. And how to calculate this number? How to calculate this number? This number is equal to number of sigma bonds plus lone pairs. Remember this always, okay? This will come handy to you while solving the numerical. I will take the numerical based on that also, okay? Sure. So the one element can represent many hybridization state. One element can represent many hybridization state depending on experimental condition. That means if you take the carbon shows 3 types of hybridization: sp, sp2 and sp3. Carbon shows 3 hybridization: sp, sp2, sp3. On the similar fashion, if you take the chlorine, chlorine also shows three hybridization. Which are those? sp3, sp3d, sp3d2, sp3d3. Iodine also. Iodine also shows sp3, sp3d, sp3d2, sp3d3. Okay? It depends on experimental condition. Okay? So these hybrid, as I already told you here. Okay? The directional properties. Now remember this point. That's why I have highlighted it in a red colored. The directional properties in hybrid orbitals is more than atomic orbitals. The directional properties in hybrid orbitals is more than atomic orbitals, and therefore hybrid orbitals form a stronger sigma bond. I have specifically wrote this point in a red color font. The directional properties in hybrid orbitals is more than atomic orbitals. Therefore, hybrid orbitals form stronger sigma bond. The directional property of different hybrid orbitals will be in the following order. Look at this. sp3d3. So how do we find out this directional property? See, more the number of directional orbitals, more the number of directional orbitals, more will be the directional property. In sp3d3, how many directional orbitals are there? 3 here, 3 here, total 6. Here 3 here, 2 here, how many? 5. Here 3 here, 1 here, how many? 4. Here only 3, which is p. Here only 2, which is also p. Here only 1. Okay, so that's how the directional properties are. More the number of directional orbitals, more will be the directional property. Okay, hybridized orbitals show axial overlapping and form sigma bond. What is my point? Hybridized orbitals show axial overlapping and form sigma bond. That means hybridized orbital never forms pi bond. Hybridized orbitals never forms a pi bond. It always forms a sigma bond. Remember this point and mark this point. Okay, hybridized orbital always form sigma bond. They do not form a pi bond. In H2 there is no hybridization, Sajid. In H2 there is no hybridization as such. It does not undergo hybridization. Okay, chalo. Let's see the types of hybridization. The very first, in sp hybridization. In this hybridization, one s and one p orbital of an atom are mixed to give two new hybrid orbitals, which are equivalent in shape, energy, known as sp hybrid orbital. And we had seen that in BeF2. Remember, we had seen that BeF2 here. sp2, sorry, not sp2, sp, spp, spp. So this is spp sigma bond, spp sigma. Okay, that's how you get the sp hybridization. In earlier case we had seen BeCl2. Here it's a BeF2. Okay, you will come to know about that, Sajid. You will come to know about that. Carbon has sp2. Yes, carbon also has sp3 beta. You will come to know that as we'll move ahead. Okay, next, sp2 hybridization. In this hybridization, 1s and 2p orbitals are mixed to give 3 new sp2 hybrid orbitals. In this hybridization, 1s and 2p orbitals are mixed to give 3 new sp2 hybrid orbitals, which are same in shape and equivalent in energy. For example, let's take the example of boron. We had seen earlier atomic number of boron is 5 electronic configuration is 1s2, 2s2, 2p1, right? You got two electrons here, one electron here. Ground state. What happens in excited state? Electron from 2s gets promoted to 2p, right? So now you have three electrons. So these three electrons, sorry, 1s and 2p, px, py. Let's consider it's px, py, and this is pz. This pz is empty. And since it's empty, it do not take part in hybridization. It's a unhybridized. This pz is unhybridized. Okay? S, px, py. So what happens now? Now this 1s and 2p, they combines to produce 3 sp2 hybrid orbitals like this. See, like this, where each has single electron. Okay, here, here, and here. Now, what will happen now? Now the hydrogen fluorine or chlorine, you can take anything. Let's take the fluorine, suppose. So fluorine comes, gives electron to form a bond. Here also fluorine comes, gives a bond. Fluorine gives a bond. So that's how you form a trigonal planar. Look at this. This is trigonal planar compound. Okay. And to this trigonal planar means it is like this. So I have a triangle like this. Okay. It is like this sp2. It is trigonal planar, and to this the perpendicular is this pz. This pz is this. It is empty. It is empty, so it will be electron deficient. It is electron deficient. Do you remember? We had seen the coordinate covalent bond. Remember? The coordinate covalent bond where nitrogen donates its lone pair to BF3. Remember? Nitrogen donates its lone pair to BF3. So it donates its lone pair to here because it has an empty d orbital. What's the bond angle? Bond angle here is 120 degree. Here also 120. Here also it has a 120. So that's how the 3 sp2 hybrid orbitals are formed. Okay. Now what is percentage S character? See, you got 3 sp2, right? So you got 3 orbitals. So percentage is, how can you calculate percentage is? You got only one orbital, which is S, and total orbitals are how many? 3. So 1 by 3 into 100, that is equal to 33.33. That is why your sp2 has 33.33 percentage S character. Okay, clear? Shall we move ahead now? Yes, dative bond, Sajid, you're right. NH3 forms a dative bond with the BF3. Okay, chalo. sp2, now sp3. Now sp3 hybridization happens in case of carbon. Atomic number 6, 1s2, 2s2, 2p2. So in the ground state, you have 2 electrons here. Two electrons here. When all orbital mix and new hybrid form, then what is the use of percentage character? You will come to know what is the percentage S character, Sajid. In the upcoming sessions, you will come to know what is the percentage of it. What is the use of it? It is not use. It is just you got sp3. In sp3, you got 4 orbitals, right? So 4 orbitals out of which one is S. So what is percentage is? 25%. Okay, but that 25% is coming, that's fine, but what's the use of that you will come to know later on. Okay, so this is ground state. Again in excited state, what happened? This electron gets promoted here, so you got 1 electron here and 3 electron in your P. px, py, pz, s, and now they will mix. They'll mix to give you 4 sp3 hybrid orbitals. And how would it look like? Here, 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 here. Okay, you got one electron. Then the hydrogen will come. Okay, I'm directly writing the bond with the hydrogen. Okay, so that's how you form the sp3. Let's write in different way. Hydrogen, hydrogen, hydrogen. Okay, this dot 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 dot, this is not a bond. Okay, this is I'm outlining its shape. So that's how the sp3 hybridization is there. Okay, so this shape is called as tetrahedral. This shape is called as tetrahedral shape. And the bond angle here is 109 degree 28 minutes. It's 109 degree and 28 minutes. Okay, so the angle between all these hybrid orbitals will be 109 degree and 28 minutes always. Okay, that's how you get the sp3 hybridization. Okay, clear everyone here? Okay, and all these 4 bonds are equivalent. Okay, all bonds are equivalent. Okay, chalo, let's move ahead. Now, types of hybridization. So we got sp3 hybridization there. Then you have sp3 dehybridization. See, in this hybridization, one s orbital, 3p orbital, and one d orbital mix to give 5 new hybrid orbitals. Okay, let's take the example of phosphorus. Again, atomic number 15, neon, 3s2, 3p3, 3d0. So in the ground state, it would look like this. 2, 3 electron, and in D you have no electron as such. Okay, what happens in excited state? We had seen earlier, this lone pair gets promoted here, and now you have 1 electron here, 3 electron here, and 1 electron in your d orbital. Okay, so now they will mix. Now they will mix. So you are having 1s, 1 px, py, pz, and 1 d orbital. All of them are mixing. And now you can see 5 orbitals are mixing. Okay, 1s, 3p, and 1d, because of which you get 5 sp3d hybrid orbitals. That's why you're getting 5 sp3d hybrid orbitals. Now how it is? How does it look like? It look like this. These are 3. Okay, they are trigonally planar arranged. Then you have these 2. So each one is having electron overlap with chlorine. This also overlaps with the chlorine. and that's how you get trigonal bipyramidal. You can see the pyramid forming here. See, this is, so this is pyramid to the upper side, to the lower side, and in between that you got a trigonal planar. That is why it is called as trigonal bipyramidal. Why? Because you are forming two pyramids now. You are forming two pyramids. One is upper, another is lower. Okay, that is how PCl3 actually forms. Out of these five, see the orbitals which are in the trigonal, the orbitals which are in the trigonal here, here, and here, they are at the angle of 120 degree. Okay, the orbital which is, these are called as axial. This is axial position. This also, this also. These are your axial position. Okay, and the three positions, this one, and this one. These are called as equatorial positions. Okay, so the axial bonds, for the axial bond, the bond angle is 90 degree. You can see here, it is exactly perpendicular to P. So if it is exactly perpendicular to P, that means bond angle is how much? It's 90 degree. Okay, and in the trigonal planar, it's a 120 degree. Okay, that's how PCl5 shows sp3d hybridization. Okay, now let's see the next. Okay, this is the same thing which I was talking about, right? I told you this is ground state. In excited state, what happens? One of the electron from the S gets promoted to D. Now you got 5 orbital, and they gives you sp3d hybridization. Okay. Yes, Sajid. 3 are 690. No, only 2 are at the 90 degree and 3 are at the 120 degree. Okay. 2 are at the 9. These two. Look at this. This upper one, this one, and this one. These are at the 90 degree. And this is trigonal planar. So this one, and this one. These three are at the 120 degree because they are in the trigonal plane now. Since they are in the trigonal plane, they are at the 120 degree. Okay. One more thing. This p chlorine axial bonds, they are longer than the p chlorine equatorial bonds. Bond length. The bond length of axial is larger than the equatorial. Why? To avoid the repulsion. To avoid the repulsion. Okay. These axial bonds, this is a trigonal plane. Okay. This is axial. This is axial. One is above the plane, another is below the plane. Okay. So to avoid the repulsion between this trigonal planar set, this axial chlorine gets elongated further. Okay, upper one also, lower one also, because of which its bond length increases, and that is why axial bonds are longer in length than the equatorial bonds, and hence they are weaker in strength. Okay, so next we had seen sp3d. Now next is sp3d2. sp3d2 happens in case of sulfur. Remember, in sulfur we can see again the atomic number of sulfur is 16. So neon 3s2, 3p4, 3d 0. So you got 2 electrons here, 4 electrons in your p, right? And 0 electrons in d. Remember that excited state. The first excited state, this electron gets promoted. Where p's electron gets promoted to your empty d orbital, and in the second excited state, first ES, second ES. In second excited state, this electron from S also gets promoted to your empty d orbital. And now you have 1s, 3p and 2d orbitals. So all of them mixed together to give you, since the 6 orbital gets mixed together, you get a 6 hybrid orbitals. So now you have sp3d2 looking like this. And then you have fluorine coming off here. Okay, the fluorine comes here. Okay, that's how you get the SF6. And here the bond angles between all the hybrid orbitals is 90 degree. Okay, so let me draw it different way. SF, 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 SF. Okay, so and this is your octahedral shape. This is your, this shape is called as octahedron. It is octahedral in shape. Okay, the d orbital which were involved here, one was dx square dash y square, another was dz square. Okay, so that is how you get the sp3d2 hybridization. It happens in case of sf6, pf6 and icl5. Okay, that's how sp3d2 hybridization is. Now we're going to move on to the last hybridization, which is, look at this, sf6. Oh, it was here only. See, this is ground state. In excited state, what happens? This electron gets promoted here, first excited state, and then first this goes, then this goes. Now you have 6 electrons in a 6 orbital. They combines to give you sp3d2 hybrid orbitals. Axial more repulsion so longer. Yes, Sajid, you're right. Okay, chalo. Now last, sp3d3 hybridization. The last hybridization which is our is sp3d3. So this is for the iodine. Atomic number of iodine is 53. So I would write 5s2 5p5 5d0. So 2 electrons in s orbital, 5 electrons in p orbital, 0 electrons in d orbital. Okay, so in the first excited state, this gets promoted first. Second excited state, this gets promoted. Third excited state, this gets promoted. So here you got 1 s, 3 p and 3 d orbital. All of them mixed together to give you 7 sp3d3 hybrid orbital. Here you get 7 sp3d3 hybrid orbitals. Okay, and it is always arranged itself in this way. This is called as pentagonal bipyramidal. This is called as pentagonal bipyramidal shape, because this is a pentagon, okay, and this is a pyramid you have here. So this is a pyramid like this. Okay, So that is how you get the IF7. Its hybridization is sp3d3. Okay, this is how it gets. ZEF6, it also shows sp3d3. Okay, so that's it for today. Okay, that's it. Finish it off. Thank you very much. In the next, we'll move ahead with this now. Okay, so bye bye everyone.